We're going to continue on with the ear now. Last lecture we covered the eye. I want to contrast the neural pathway between vision and hearing. So this was what was on the whiteboard last week, Tuesday, neural pathway for vision. The only thing I added is, this is the point where the optic tract enters the brain. So this is outside the brain, this is in the brain. Okay. Did we leave off here? I don't remember.
Yes.
Okay. So we're in the middle ear. Again, the function of the middle ear is, for hearing anyway, is to amplify the sound 22 times. Also in the middle ear, you can see the round window. The round window and the oval window is the border between middle ear and inner ear, both those windows. Now remember in lab, we're going to cover it here in just a bit, but remember in lab the three chambers in the cochlea, scala vestibuli and scala tympani. That is what is on the other side of these windows. On the other side of the oval window is the perilymph of the scala vestibuli. What I'm saying here is on the other side of the round window is the perilymph of the scala tympani. Okay. Oval window, round window. You can see how that, here in light blue is the middle ear. Here in dark blue is the external ear. Here in green is the inner ear. You can see how the oval window and the round window is the border between middle ear and inner ear. Everybody see that? And this is showing you what's on the other side of those windows. On the other side of the oval window, perilymph, the scala vestibuli. On the other side of the round window, perilymph of the scala tympani. Can you see that in that figure? Now, this is what we would call in lab the base of the cochlea. It actually goes around 2.5 times. This is only going on 1.5 times. It actually goes 2.5 times. Are you following me? But when you get to the apex, look at the green and the blue here. Scala vestibuli is in green, scala tympani is in blue, and look what happens at the apex. One runs right into the other. It is actually the same chamber. But at any one point in the 2.5 turns, it looks like 3 chambers. In reality, there's only 2. The chamber that has the endolymph, scala media or cochlear duct, they're in yellow, and the other 2 that have perilymph. They are actually the same chamber because they join at the apex. Does everybody see that? The auditory tube connects the tympanic cavity to the nasopharynx. This is what is used to equalize barometric pressure. So when you go up in elevation, the pressure in your external auditory canal goes down. The auditory tube is normally collapsed. It's a very soft, floppy tube. Rarely is it actually wide open. It's usually collapsed. But when you get up into the mountains, your tympanic membranes are actually bulging out because out in the external auditory canal, the pressure is less. It was the same in the tympanic cavity. It bulges out, and that's why you gotta chew gum or yawn, and you pop it right back into place. Everybody's experienced that, right?
Yeah.
So when you look at this, here it's showing you how when you're coming back down, the opposite thing is happening. So it's both going up and going down. You have to chew gum or yawn or something to snap open the auditory tube, and it equalizes the pressure, and all of a sudden the tympanic membrane goes back. While it's bulging in or bulging out, it's kind of hard to hear, isn't it? Also, have you guys noticed that when little kids get colds, how they get middle ear infections a lot more than adults?
Yeah.
Have you guys ever noticed that?
Yeah.
That's because their heads are small. When you have a cold, you're gonna probably have an infection in the throat. Nasopharynx is part of the throat. Pharynx means throat, and there's 3 subregions. We're gonna learn about this later. Okay, this is the superior region of the throat, the nasopharynx. Everybody say that out loud. Pharynx.
Pharynx.
Pharynx. Look how it's spelled. It's underlined right here. Pharynx. Everybody see that? Okay. Nothing screams out, I didn't pay attention in school, like calling it pharynx. If you call it pharynx, you're telling everybody I didn't pay attention. Are we clear?
Yeah.
So if you ever go out in the clinic floors and call it pharynx, don't ever sandwich your teacher. Are we clear?
Yeah.
Pharynx. All right. Also open to the tympanic cavity is the mastoid air cells. Now, the reason why we don't call it a sinus, even though that's what it is because it doesn't open up to the nasal cavity. It opens up to the tympanic cavity. So we call it mastoid air cells, but it's basically a sinus. The mastoid process, that big bony bulge that looks like a drooping boob, that's why it's called mastoid. It's hollow, because like every place in the skull where the bone is thick in 3 dimensions, it's hollowed out. The mastoid process is hollow with mastoid air cells. So little kids, they can get middle ear infections a lot easier because the auditory tubes are so much shorter. In adults, that infection is growing up in here, and you've got various, your immune system is fighting it back, and you got rid of the cold before it reaches here. You don't have a middle ear infection. Well, here's the nasopharynx starting with a kid, because they're a lot smaller. When that throat infection starts going up the auditory tube, it's there before they can fight it off, and that's why kids get more middle ear infections. Does this make sense? And that's why also kids tend to get more mastoiditis, because then it can spread up the opening from the tympanic cavity into the mastoid process.
So is the nasopharynx that's shorter, not their?
The auditory tube is shorter. That's basically inflammation. Itis means inflammation of. So it technically means inflammation of the mastoid process. Any questions? All right, we're ready to go to the inner ear. Remember, there's a bony shell, technically part of the temporal bone, it's not its own bone. But we call that the osseous labyrinth. We've actually dissected some out in cadavers in the past. I don't know if they're ever gonna do that. Again, I have to really think about if I have the energy to think about doing that again. But we did complete surgical nervous system extractions. We had to obliterate the skull to get the brain and the cranial nerves out. And while we're doing it, we opened up the temporal bone, and that's what it looks like. Over there on the left. Paralleling the osseous labyrinth is a membranous labyrinth. It's just a thin, waterproof sac. In it is endolymph. Outside of it is perilymph. So perilymph is outside the membranous, inside the osseous, between the labyrinths. Perilymph is very similar to CSF chemically. It's very similar to CSF. Endolymph is freaky because it's an extracellular fluid, but its contents are very similar to intracellular fluid, and it's one of the only ones that are like that. Not that that'll be on a test, but I don't know. Maybe you guys are interested. There it is. The brown is the osseous labyrinth, the bluish gray is the membranous labyrinth. Okay, there are 3 regions of the inner ear. And we're gonna go over them. There's a lot more to this than what I'm gonna cover, but the PowerPoint is telling you what you're responsible for in lecture 2 and 3. Each of the 3 regions, and only one has to do with hearing, but each of the 3 regions have these things called hair cells. And they have look like little tufts of hair on it. They are not hair, they're cilia, okay? These cilia don't move on their own, but things do move them. And when you bend the cilia, that's what triggers an action potential that go up to your brain. Everybody got it?
Mm-hmm.
All 3 regions of the inner ear, the cilia are embedded in jelly. All 3 regions of the inner ear, the cilia of the hair cells, are embedded in jelly. And each has a different name. All right. Let's start out with the semicircular canals. So there's semicircular canals, vestibule, and cochlea. 3. Semicircular canals on each side are 3. And they are arranged in 90-degree angles to each other's in 3 dimensions. So that means boom, boom, boom. And because of that, they can detect any rotation, any gyroscopic rotation in any plane, in any 3-dimensional plane. Your brain can tell the difference. At the base.
What do you mean by that? I don't understand that.
Your brain can tell the difference. Even if your eyes are closed,
Oh, you're
your
wrong.
brain can tell the difference.
Way to go.
Yeah, so if we're out, you're driving in the car, you only have to worry about 2 dimensions.
Uh-huh.
If you're a fighter jet pilot, you have to worry about 3 dimensions.
Okay, got it.
All right, at the base of each semicircular canal, there's an ampulla, so on each side there are 3 ampullae. Inside of that swollen area is a structure we call the crista ampullaris. And on the crista ampullaris are the hair cells. The cilia of these hair cells are embedded in a jelly-like sail called the cupula. So in the case of the semicircular canals, the jelly is the cupula. You need for me to write this down?
How can they move if they're stuck in jelly?
Because the jelly moves.
It's like a mucus fluid.
Well, it's not liquid. It is actually solid jelly, but it gives and it moves. Okay? So. The inner ear, semicircular canal. Hair cells. Crista ampullaris. Cilia. Embedded in the cupula. Okay? Cupula, it says there's gelatinous. It is jelly-like. And basically the endolymph, which is because right in the center here is the membranous labyrinth. Can everybody see this thin line? That's the membranous labyrinth. That means there's perilymph between the bone, osseous labyrinth, and the membranous labyrinth. But inside the membranous labyrinth is endolymph. Everybody see that? It's the endolymph that moves the cupula. If the cupula moves, the cilia get bent.
Okay.
Everybody got it?
Okay.
So for example, here's 3 hair cells. It's got cilia embedded in this green cupula. If you spin or turn, the endolymph is going to move the cupula. That bends the cilia, and your brain knows it. Okay, so we do this one thing in physiology where, and I told you that this gets really complicated from here. This is all you gotta know for lecture exam 3, but it gets really complicated, and it goes to various nuclei in the brain, and involves 3 other cranial nerves that move your eyeballs, which allows you to track a moving object even if you're moving in a different direction at a different speed. Do you remember me saying that on Tuesday?
Yes.
It's very, very complicated. This is a good example. Some of those nuclei are also getting information from your semicircular canals and vestibule. Okay, so the best way to understand this is, say I got a glass of water here, but there's something floating on this side. And I got ice cubes, so I can't really see it that well, so I want to see what it is that's over there, and I go like this. What happens?
It turns around the same back to the other side.
The glass turns, but the water doesn't. The water lags behind. Have you guys ever done that?
Yeah.
Glass turns, water lags behind. But there is friction between the glass and the water, so if you keep turning it, eventually the water comes around. Then you stop turning the glass, and what happens? The water keeps going. Follow me? If we're talking about the horizontal semicircular canal and I put a student in a stool and spin them, the same thing happens. I start spinning them, the endolymph lags behind, the cupula bends. It's giving your brain information that you're moving. Everybody got it? But if I keep spinning, and I'll spin the student 10 times, eventually the endolymph catches up to the osseous labyrinth. And now they're moving together. When they're moving together, this cupula that was bent because the endolymph lagged behind is now caught up. And it's actually telling the brain I'm not moving. Now there's other inputs going to the brain that says, yeah, I'm still spinning, but not the semicircular canals. Are you following me? After 10 spins, I suddenly stop the student, and the endolymph keeps going. And now the cupula is telling the brain, I'm moving, except the student isn't moving, because our brains feel nothing. They're only receiving action potentials, and it confuses the hell out of the brain, because I have the student open up their eyes really open after they stop spinning, and the eyes are doing this. I'm moving, no I'm not, I'm moving, no I'm not, I'm moving, no I'm not, because the visual field isn't moving, but the cupula is still bent. I'm moving, no I'm not, I'm moving, no I'm not, I'm moving, no I'm not. It's called vestibular nystagmus. And it's because of this semicircular canal in the endolymph. We've got the vestibule with the utricle and saccule, which is closer to the cochlea. The utricle or the saccule? Saccule. How do you remember it?
It's not a veil.
Because it's a boy snail. See? That's why you gotta remember some of these things. Even though it's not true, you always get it right. Okay, hair cells.
Are the hair cells also in that jelly, or is it just the cilia on there?
Just the cilia are in the jelly. They're embedded in. Smell right. Okay, all 3 regions are very similar in that they have hair cells. Here, the hair cells are located in a thing we call the maculae, and that's one of the things, microscopic images you need to know for the lab exam next week. Ventricular macula, that's where the hair cells are. The cilia are embedded in this jelly-like membrane that have rocks in it. The rocks are called statoconia or otoliths. The rocks give the membrane, this jelly-like membrane, mass, some weight. Now, one of the things that we'll talk about here in just a second, that the semicircular canal sense is something we call dynamic equilibrium, because a turn is, from a physics standpoint, very dynamic. On the vestibule, like in this picture, all you gotta do because of gravity is tilt your head. Or, and so we call that static equilibrium, even though that's some kind of a misnomer. Okay. But all you gotta do is tilt your head, and because these little rocks, statoconia or otoliths, have weight to it, it causes this whole jelly-like membrane to sloop down because of gravity. Everybody got it? But notice that bending of the cilia in that picture. The same thing happens if you're in your car and you step on your brakes. The membrane's going to sloop forward, just like that. Everybody see it? Understand it?
Even without you moving at all.
That's right. Just from inertia, and that's actually what the statoconia is doing, the membrane is mass for inertia. So you could do this, or step on the brake. Or you can do this, and step on the gas. The otolith membrane moves the same. Everybody got it? That is the technology of Star Tours at Disneyland. Right? Everybody been on Star Tours or a ride like that?
Yeah.
They show you this TV screens that look like they're wheeling in this little star speeder. And you wait forever and you finally get on. It looks like there's this big screen, a windshield. And the windshield, it's a 3D movie screen. And that's why you have to put these space goggles on now, because those are 3D glasses. And they're playing a 3D movie on the screen. And when you jump to light speed, oh, and you're not getting into a star speeder, you're getting into an elevator with 3 hydraulic lifts. And as soon as you jump to light speed, the room goes like this, just like when you step on the gas. And you watch this image of accelerated lights while your maculae is doing this. Boom. You come crashing into the space station at the very end. They show images of rapid deceleration, and the elevator does this. Just like that. Same thing with all the little turns, they just lean you. And your brain, because your entire existence as a human being is a brain-generated illusion, goes with it. And you have stayed in that building the whole time.
So it's always I'm gonna call it the rock, it's always the rock either going with inertia or against inertia? Like forwards or backwards, it has nothing to do with side to side?
It does not, that's semicircular canals.
Oh, okay.
The other thing that the vestibule will do is also vertical, like riding in an elevator,
Down.
right? But if you're on gravity going up and down in an elevator, your proprioceptors will also give you information, like if you start to go up in an elevator, you suddenly get heavier. All the proprioceptors are giving your brain information, just got heavier. As soon as you reach the floor and it stops going up, you suddenly get lighter.
So when you go up though, are those rocks technically going up, or are they still kind of falling forward a little bit or backwards?
They're still doing this, but I can't remember which one now. I think it's the sacule that does vertical. It's just arranged in a certain way that it's more vertical, it's gonna cause it to swoop up and down.
Okay,
Where the usual goes more this way,
okay.
okay? But turning is semicircular canals. Any questions? Did I just ruin that ride for you?
Yeah.
Bullshit, you still go on it. All right, here it is. So we called static equilibrium for the vestibule, dynamic equilibrium, because turnings are quite dynamic. This is showing you some of the more complicated pathways that are involved in vestibular nystagmus. You don't need to know for lecture exam 3, but in case you didn't believe me, there it is. And you can see how it's affecting the 6 extrinsic eye muscles. That's why we can see bending cilia and how it makes you move your eyes. Now let's go to hearing. So this is the only one that has to do with hearing. So out of the 3 regions of the inner ear, only this one has to do with hearing. Hair cells are in the spiral organ. It should be called organ of Corti. And the cilia cilia for those hair cells are embedded in this jelly-like patio roof we call the tectorial membrane. So all 3 regions of the inner ear have collections of hair cells. You gotta know where they're located. And the cilia, which is where they get their name, hair cells, are embedded in jelly. All right. So the cochlea, it looks like a snail. These chambers are rotating around the hub 2.5 times. The name of the hub is the modiolus. Part of the osseous labyrinth that spiral and radiate out of the modiolus is called the spiral lamina. The spiral lamina is part of the osseous labyrinth. And it basically organizes this cochlea. So the central hub is modiolus. So base, coils, and apex. Here's the name that a lot of textbooks use for apex, helicotremor. Modiolus is the central bone, but this little shelf that's headed right for the spiral organ, which is part of the osseous labyrinth, is called the spiral lamina. It radiates out, heading straight for the spiral organ. All right, so at any point in the 2.5 turns, if we cut open the cochlea, it looks like 3 chambers. Remember, in reality, it's only 2, but it looks like 3 chambers. The one on top is the scala vestibuli, the one on bottom is the scala tympani, and the one in the middle is the scala media. The scala media is the membranous labyrinth. That's why there's endolymph in the scala media or cochlear duct. Perilymph in the other 2. And that's why there's perilymph in the other 2, because it's the same chamber. That perilymph flows right from one to the other at the apex. Notice that thin membrane that's separating the scala vestibuli from the scala media is simple squamous. That's it, in a basement membrane. And that's that thin vestibular membrane. Everybody got this slide? Everybody got this? And there's the vestibular membrane right there. Now, separating the scala media from the skeleton tympani is a much thicker basilar membrane. Sound waves don't go through the basilar membrane, but it does go through the vestibular membrane. I'm gonna change this whole lot.
Is that just cause it's thicker?
Yeah. That's right. Okay. Sitting on that thicker basilar membrane is the spiral organ, where the hair cells are. Now again, because these cilia just have to bend, it's a physical deformation, these receptors, all of these receptors, are mechanoreceptors. You're just bending cilia. Everybody got it? All of them. That's what it says, is where mechanoreceptors appearing are found. All the hair cells are all mechanoreceptors. All you're doing is bending cilia. If you are hearing the sound of my voice, it is not your brain hearing me. It is, there are hair cells in the cochlea that bend at a certain part. That's going to cause there to be an action potential that goes to the temporal lobe. Then your brain generates an illusion of sound. Everybody got it? Any questions? All right, sound waves are like all waves, and all waves have different size waves and different frequency of waves. Amplitude and frequency are the two parameters of measurements of all waves. It could be sound waves, light waves, brain waves in an EEG, or ocean waves. All waves have amplitude and frequency. So the only difference between this and this is that there is greater size troughs and crests with loud volume. The only difference between this and this is when it's higher, there are more crests. That is amplitude. That's me talking softly. That's me talking louder. That's amplitude. Everybody got it? This is the crest. If I have that many crests in this amount of time, and actually because sound waves, by the way, have the same speed through air, I can also think about frequencies, how many crests not per second, and how many feet as it's traveling through air. Everybody got it? Everybody, pay attention to this, people. Because that new Star Wars movie's coming out. There is only sound if you have media to carry the waves. In this room, it's air, which is different than underneath the swimming pool. You can actually talk to somebody underwater, but it sounds different. And also the sound doesn't carry very far in liquid. It carries a lot farther in air. But if you don't have a media to carry the sound waves, there is no sound. There is no sound in space, people. It is dead silent. So remember that when you're watching Star Wars. But this would be the same volume. But a lot lower. Everybody get frequency and amplitude? You got 5 in this space here, you only got 1.5 in that space here. That's frequency. How do I explain this? How do you guys want me to explain it?
As best you can.
Okay, the frequencies of human hearing are 20 to 20,000 hertz. Hertz is cycles per second. Everybody got it?
Just how fast?
How many crests per second, or how many crests in feet? This is actually the ideal hearing range for humans. And probably by the time you're done with kindergarten, you don't hear this anymore. As you're growing up, you're losing it on both edges. By the time you hit adulthood, yeah, it's probably more like 28 to 19,000 hertz. Everybody got it? Everybody look at me. This might be boring science to you, but if you know it, you don't ever get ripped off by car stereo salesmen or any audio equipment. You cannot get ripped off if you know the science, because they're going to try to upsell you. Hey, you got to buy this thing, man. It goes 14 to 24,000 hertz. It's way better than this other one. Oh yeah? I'm not buying it for my dog, because that's the only one in my house who can appreciate the difference. I can't. I'm at 28 to 19,000 hertz. Why do I want to spend more money on something that has a wider range? I cannot hear the difference. Are you following me? This is not boring. Knowledge saves you from being ripped off. Okay. So, we have to talk about this thing called resonance. This is where all the troughs and crests line up and kind of boom. That's the spot of resonance. If I had a Corona bottle here, I can blow in on the top of that opening. Well, I'd have to open it first. And the sound of the wind going in the chamber will resonate, and that's what gets you a whistle. Whistle is getting you a resonance of sound. Everybody got it? And the more sips of that Corona I drink, you would notice the sound getting slightly deeper, because the chamber volume is now different. Now a different frequency is going to resonate. Everybody, just remember the Corona bottle example. Can you imagine that?
I can imagine on me though, like is my ear the opening to the Corona bottle? No.
Because this is now in liquid, remember, because this is all perilymph and endolymph. But notice when you look at the 3 chambers, as it goes around the hub, how they are getting progressively smaller as it gets to the apex. That is the same thing as far as the differences in the whistle as I drink more Corona. The size of the chamber is changing as I'm drinking the beer. That's what you do when you whistle, by the way. You're changing the volume in your mouth so you can hit different, or you can resonate different tones. I'm just changing the volume, but the sound is from resonance. Are we clear?
Yeah.
Okay, that is how you can tell the difference between this and this, because your brains hear nothing. I'm going to show you how you can tell the difference. In the 2.5 times around the hub, the higher frequency sounds resonate closer to the oval window. The lower frequency sounds resonate at the apex, the helicotrema. And it's just what spot in the 2.5 turns does it resonate. And that's the different hair cells that are gonna bend. If it's higher, the hair cells bend closer to the oval window. If it's lower, the hair cells bend further closer to the apex. That's the only reason why you can tell the difference between notes.
So each 3 parts have a different resonance, and it's not just boom, 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 it just gradually changes to the apex?
Now, let's see.
Each 3 of those has a different level of,
Like this, okay, so I've straightened out the cochlea, so it doesn't even turn at all. Higher frequency tones are gonna resonate here, lower frequency tones are gonna resonate there.
but it's gradual is what I'm asking.
It is, it's graded all the way up. From 20,000 hertz to 20 hertz at the apex. Except as you grow, because of the size and the shape of the chambers. As an adult, this is gonna be more like 19,000 hertz, and this is gonna be more like 28 hertz. Everybody got it?
That's why we're losing it, cause it's growing bigger,
It's because of the shape and size of it.
so we don't physically lose something,
No, well, you can, but not necessarily.
like a body part.
Right. 20 to 20,000 hertz is the ideal range of human hearing, and most people lose it by the time they're 5. Everybody got it? Don't be upsold. Just don't. Okay, well, at that point of resonance, it's actually kind of violent in the cochlea, and that is where the basilar membrane gets bent, there and only there. And when it moves up, it squishes the cilia against the jelly-like tectorial membrane. That's where it bends. Oh, here's a possible question, essay question. I'm gonna erase this amplitude and frequency. Everybody kind of understand what amplitude and frequency is about waves? Again, it's the same thing with EEG waves or ocean waves. Amplitude and frequency. Okay. If you're hearing the sound of my voice, let's walk through what structures the sound waves are going through. They're getting caught in the auricle. External auditory canal. Tympanic membrane. Malleus incus stapes. Oval window. So far so good? So this is the border line from middle ear in blue, so this is middle ear. It's external ear. Inner ear. On the other side of the oval window, there's a perilymph of the scala vestibuli. Remember that the vestibular membrane is really, really narrow. And so it's just gonna go right through it. What's on the other side of the vestibular membrane? Endolymph, the scala media. Sound waves are going through scala vestibuli and scala media at the same time. Now, it's at the point of resonance. Okay, because eventually it's going to hit the spiral organ. And at the point of resonance, or some waves can go all the way to the apex. Also called helicotrema. Then what's going to happen to the sound waves?
Go back out to the perilymph, from the scala tympani to the round window.
It's got to go out the perilymph of the scala tympani and die out in the round window. Okay? So now let's look at this picture right here. These are sound waves. It's going through the scala vestibuli and the scala media at the same time. And at the point of resonance, it's going to do a U-turn and head out in the perilymph of the scala tympani. Some sound waves will go all the way to the helicotrema and then come out the perilymph of the scala tympani, which dies out at the round window. The round window, when it catches the sound waves, it just bulges out and the tympanic cavity kills the waves. It is actually the equivalent of the outer pigmented layer, the retina. The pigmented layer is to absorb the light, so it only, as the light's going through, only stimulates the rods and cones once and dies out. Same thing here. Sound waves, you only want it to do this once, and then it dies out there. Say if you do have a middle ear infection, you had a bad cold so bad that it actually got, adults do get middle ear infections. And it gets all full of snot. And then as it dries out, the snot is right up against the round window. And now the round window, instead of bulging out and absorbing the sound waves, it just hits this wall of snot and comes right back into the cochlea. If that happens, you will hear an echo. Because the sound waves are going to come in and stimulate and resonate twice. Does this make sense? Does anybody ever experience that? Any questions?
So you're saying.
Tracing the sound waves through the ear all the way out to the round window is a potentially large essay. So there's 3 potentially large essays, of which I'll ask 2. Questions? All right, well, let's do the neuropathy, because this is a little different. Does this help at all doing this on the whiteboard? You guys just don't want me to fill in blanks on the slides? This is a little bit different. There's no ganglion cells. The hair cells are actually synapsing with the dendrite of the bipolar neuron. This right here in blue and these guys here are actually the dendrites of the bipolar neurons. Let's see if I got another picture of this. Okay, here's the hair cells here. They synapse with the dendrites of the bipolar neurons. Everybody see all these little strings coming out here? Those are all dendrites of the bipolar cells or bipolar neurons. Remember, these three chambers are going around 2.5 times around the hub. These strings are going around 2.5 times around the hub. On the other end of that dendrite is the cell body of the bipolar neuron. So there's going to be a collection of bipolar cell bodies going around the hub 2.5 times. That is the spiral ganglion. Spiral ganglion is the cell body of these bipolar neurons. These are all the dendrites. They cut it off right at the cell body. And it's going around the hub 2.5 times. Are you following this? Also, the axon of that cell body, of that bipolar neuron, is the cochlear branch of cranial nerve 8.
Can you say that again?
Right here. The axon is the cochlear branch of cranial nerve 8. So when we talk about the cranial nerve here for vision, it's the axon of the ganglion cell. When we talk about the cranial nerve here, it's the axon of the bipolar neuron. It's different. Also, these bipolar neurons don't fire action potentials. They only do what we call graded potentials. That one does. And it enters the brain and goes to the cochlear nucleus. And it's going to be a little bit different, especially as it talks about the inferior colliculi. Whereas in vision, it branches. This one doesn't. It will do some decussation. You remember what that means? But instead of branch, it's in the same line. Then it's going to go to the thalamus, because all senses except for the sense of smell synapse in the thalamus. But instead of the lateral geniculate body of the thalamus, this is the medial geniculate body of the thalamus. Looks very similar to vision, doesn't it? Then it's going to direct things to the temporal lobes. So a lot of this is similar. We're in the corpora quadrigemina, that's superior colliculi, this is inferior colliculi. That's the lateral geniculate body of the thalamus, this is the medial geniculate body of the thalamus. A lot of these pathways are barely functional at birth. And they are actually being fine-tuned in the neonatal months. And you can see it happening. You know, that baby comes out and they're just can't focus on anything. Pathways are maturing. And pretty soon, with a few weeks, the baby can start to actually focus on things and track things. Eventually, loud noises are not so scary. One of the reasons why they think that loud noises are so scary for neonates, newborns, is with these pathways still not mature, that young neonates can actually see loud sounds. It actually causes there to be light or shaking or something with their vision, which is, if that happened to you, you'd probably cry too if there was a loud sound. Okay, we got a couple more senses to consider, and we got to cover endocrine, and I think that might be it for lecture exam 3. All right, olfactory sense. Again, this picture, and a lot of things on the internet are like this, is upside down. Olfactory epithelium is on the roof of the nasal cavity, not the floor. The free space should be on the bottom. Everybody got it? Here you're gonna have chemoreceptors. These are not mechanoreceptors like in the inner ear. These are chemoreceptors. They have cilia just to increase surface area. So you have olfactory receptor cells intermixed with supporting cells in the olfactory epithelium. Supporting cells, olfactory receptor cells are both underlined. Everybody see that? And as we saw in the pictures in lab, it's on the very roof, which is the undersurface of the cribriform plate, the very superior portions of the nasal septum, as well as the superior nasal concha. That's where we find it. Especially important for us, since our sense of smell is really stunted compared to other mammals, we need to create some turbulence in the nasal cavity to increase the chances of one of those hairs catching a chemical. That's why sniffing increases your sense of smell. It's to create turbulence. In order for you to smell something, you have to have that chemical diffuse through a layer of mucus. If it cannot dissolve and diffuse through a layer of mucus, you can't smell it. That's why certain things are odorless. Everybody's heard about, oh, this chemical's odorless? It's because it can't get through the mucus layer. Everybody got it? And you can discern thousands of different scents. Now this is what I was talking about in lab, but let me put this over here. Olfactory pathway and gustatory pathway are a couple of possible short estimates. So, cranial nerve 1 is actually going through the cribriform plate. And this is what I was telling you in lab. You know, we use the models and we say, oh, the olfactory bulb and the olfactory tract, that, and we call that cranial nerve 1. It's not. See, look at this picture. The blue nerves are cranial nerve 1. In the olfactory bulb are second order neurons that we erroneously say, okay, well, we can't pin those little guys going through the cribriform plate, so we'll call this cranial nerve 1. No, olfactory bulb and olfactory tract are second order neurons. The blue ones are cranial nerve 1. So then it'll go from that to second order neurons, olfactory bulb, that's going to go to the tract. I'm going to use abbreviations. Olfactory tract, and that's what enters the brain. Okay? And this is the one sense that does not synapse in the thalamus. It goes straight to the olfactory cortex and the limbic system. Okay? This is the only sense that reaches the cortex without synapsing in the thalamus. Here, since I put all the T's underlined in red, I'll just say no thalamus. Parts of the hypothalamus are limbic system, so it's and also this is the reason why certain scents will have a real base emotion to them, because that's what the limbic system is, it's kind of the brain base emotions. And that's why certain scents you can remember like was yesterday, because that's also where long-term memories live. Is this starting to make some sense? I gotta get through this. I used to tell a story from my clinical days on this, but I'm gonna go on. Everybody got this?
So this is the essay?
Yeah, short one. So things like, the 5 steps of the reflex arc, or some of the other short ones. Yeah, I can't remember. Should be in your notes. You gotta remember. Okay? Everybody got this one?
This whole, so you're saying that this slide is the short essay, also a short essay, or not?
So like in lab, you want us to identify the olfactory as, the cranial nerve.
Yeah, so we're gonna use the olfactory bulb and tract as cranial nerve 1.
In lab, but in
In lab.
lecture, do you want us to identify that it's the nerves that are running through them?
The cribriform plate is the olfactory nerve. But that's the actual truth.
Okay. And are all those little tiny holes in the bone, what they're running through?
Uh-huh. Yeah. In this animation, the blue neurons are cranial nerve 1. What's in the olfactory bulb and tract are second order neurons. Are we clear on that?
Yeah.
But I can't pin this in lab, so if I pin the second order neurons, just call that cranial nerve 1. Are we clear? Are we clear?
Yes.
Everybody got that? All right, let's talk about the sense of taste. Go ahead and feel this. We're gonna concentrate on the gustatory receptors on the tongue. There are some in the throat, in the pharynx, and actually with that which is in the pharynx is actually we'll use cranial nerve number 10, but so there is cranial nerve number 10 involved, but it's so minor and it's only down for taste buds in the throat. What's on the tongue is actually 2 cranial nerves. Now, even though you can sense thousands of different smells, you only can taste 4 tastes. Everybody got it? And that's, they're listed right there. How come you could tell the difference between Pinot and a Cab if all you have are 4 tastes? How can you tell the difference between barbecue chicken and roasted chicken? Or chicken teriyaki? Your brain melds olfactory and gustatory together. That's why if you have a cold and your nose is all plugged up, why all food tastes bland, because you just went down to 4 tastes. Does this make sense? Okay, so I'm just gonna concentrate on the gustatory pathway off the tongue. These taste buds are found in the crevices around these bumps on the tongue called lingual papillae. There are 4 of them, but notice only 3 are highlighted. Those are the ones with taste buds. Filiform papillae do not have taste buds on them. They will also have chemoreceptors, what are called gustatory cells, intermixed with supporting cells. And they're unknown. And you don't need to know that this is the chorda tympani branch of the facial nerve. Just know that the anterior 2/3 is the facial nerve, cranial nerve 7. Posterior 1/3, cranial nerve 9. The gustatory cells don't have cilia like the olfactory cells do. They have microvilli, still though to increase surface area. We're kind of covering a lot of material in these lectures, huh? Have you noticed that? That's because we're not on lecture exam 2 anymore. And also, I've actually had to accelerate how much material I cover for the next few weeks so that we could take Thanksgiving week off.
Oh, are we gonna have open lab? They said open lab that day on Tuesday. Is it gonna be available?
On the day that I normally would have Tuesday lab?
Yeah.
Sure.
Okay, yay.
I'll have to manage them, so I don't get the day off. Well, I mean, if you guys are willing to do open lab on
Yeah.
Tuesday before Thanksgiving,
Yeah.
if you're not taking the day off, then I should take the day off. Okay, the neural pathways and address, 79 Mott Place. That's the kind of stuff I would do as a student. 7 is facial nerve, anterior 2/3 of the tongue. 9, glossopharyngeal, posterior 1/3 of the tongue. It goes to the medulla oblongata, then to the thalamus. Again, all senses except olfactory, synapse in the thalamus, ending in the parietal lobe. Again, this is for tongue, taste buds only. For the gustatory cells that you find in the throat, that'll go up the vagus nerve, cranial nerve 10. But for lecture exam 3, this is what I'll ask you, if I ask you. Like that, 79 Lot Place? Okay, any questions? So there's like 3 possible big essays. This is one of them. And there's like, what, 4 possible little essays? This is 2 of them. I think the other 2 are 5 steps of the reflex arc. And the 2 sets of 4 we talked about on Tuesday. Everybody got it? So I don't, when we do the exam review, I don't have to go over possible essays. I just covered it. Okay. All right, last topic for lecture exam 3 is endocrine. This is where I'm going to cover it. There are 4 chemical classes of hormones. The first one is the steroid. Now this thing that has 4 rings, 6, 6, 6, and 5. Everybody see that? That's the classic structure of a steroid. It actually used to be a long chain fatty acid. You guys remember the phospholipid that I drew up? And the long hydrocarbon chain that, because it has 2 tails? Take that one tail, make it do a U-turn, come back around and form cross bonds, and now you have a steroid. But it used to be a single long chain that got bent, it came back around after doing a U-turn, and it formed 4 rings. And that is why it is lipid soluble, because it used to be a fatty acid, and everything that is lipid soluble can go through cell membranes, because the vast majority of the phospholipid bilayer is lipid, fat. Then the second one is single amino acids, or they could be 2 amino acids, but they're really tiny, so we call them amine hormones. They're really small. And because they're really small, these also can cross the phospholipid bilayer. One, because it is lipid soluble. The second, because it's really small. Okay. Here we can see for thyroxine, it's actually 2 tyrosine amino acids. So it can be either 1 or 2. Everybody see that? This bottom figure? These are 2 tyrosines. And it gets put together in thyroxine. Those little green circles, that's iodine. Thyroxine is only functional if it has iodine on it. In other classes, you might see the designation T3 or T4. That's how many iodines are on it. So what you see here is T4. Hey, everybody got it? The interesting thing is the T4 is the transporter form in the blood. It does nothing. But once it's in a cell, it's got to lose one of the iodines to actually cause your cell to pick up the speed as far as metabolism goes. All right, then we can get several amino acids together, but it's still rather small. But even though it's small, it's already too big to pass through cell membranes. And here's 2 good examples of polypeptide hormones. These come out of the posterior pituitary. They're only 9 amino acids long. Can you see that? Hormones show great specificity. And you can look at this picture with a critical eye. You might be too tired to do that right now. But out of the 9 amino acids, 7 of them are identical. There's only 2 out of the 9 that are different. Can you see that? Number 3 and 8? The rest of them are identical. And just by changing those 2 amino acids will be the difference between retaining water or spitting out a kid. Then if we get a big chain of amino acids, those are protein hormones. Both of these do not cross cell membranes. They're too big. Only the 2 on the previous slide can cross cell membranes. And that's why this is important. This is why this is important. For the first 2, steroids and amines, okay, by the way, the hormone is the first messenger. The hormone is the first messenger. The hormone is the first messenger. The hormone is the first messenger.
Okay.
And because of that, for the first 2, since they can go into cell membranes, you only need the first messenger. There, steroid goes right in, it has to bind to a receptor inside the cell, and it's a combination of the steroid and receptor that sets the cell in motion. But here you can see, oh, here's the T4 that's out in blood. It's gotta lose one of the iodines to become T3 and then binds to a receptor, but it crossed right into the cell. Everybody see that? It is for the 3rd and 4th types of hormones that we need a second messenger. Okay? But for the first 2, you just need the first messenger with the receptor. The hormone by itself doesn't do anything. It's only when it binds to a receptor that it sets the cell in motion. By the way, that's what hormone means. It comes from the Greek word hormone, to be set in motion. Okay. The ones that cannot cross needs a second messenger, because they never enter the cell. They bind to a surface receptor, that activates an enzyme, adenylate cyclase, and produces cyclic AMP. You guys remember ATP? And what's this called? ADP. And what's this called? AMP, monophosphate. I need more whiteboard. This enzyme called adenylate cyclase causes there to be 2 bonds to the phosphate group, to the ribose. There's only 1 here for regular AMP. This is cyclic AMP because there is a circle of bonds. Everybody see that? That's the second messenger, and that is what sets the cell in motion. The first hormone, the first messenger never enters the cell. It's too big. Everybody got it? Oh my gosh, I think we're out of time. How many slides do we have left?
4.
guys are gonna have to fill them out yourself. Okay? Bring it next week.